I was intending to introduce myself, but Craig's already done that. But I will spend a minute just reflecting on this title I created, asked some colleagues, and we came up with this sort of quirky twist of words. Anyone in industry, in engineering, even probably from school, you recognise what WATT is. It's a measure of energy. But if you read it, it's where's the next watt? And hopefully by the end of this little session, you might be able to recognise what the watt, when it's spelled W-H-A-T, might be. So I approached this talk based on just some simplistic reflection on the amount of energy that we actually use. And because my PhD was in vehicle efficiency, I went down that path. Now the background image there is the car, well, not the actual car I own, but the same as the car I own. And based on average fuel consumptions and average distance travelled for a typical vehicle in Australia, that calculates to be 4 litres of fuel a day. You might already know that based on the fact that it's about $6 a day, or you put your $40 worth of fuel in the car a week, or however you could justify that number. That's the number that we're using as a premise, and it's just only an average. It isn't supposed to be representative of anything else. So the bottom line to this talk is that we jump in our car every week or two. We go to a service station and give them some money, and then we drive away, and we really don't have any sense of the amount of energy that represents. So that 4 litres of fuel, in fact, most nearly all liquid hydrocarbons that you can burn, they have very similar amounts of energy. If you were to be able to measure the energy represented as heat when you burn the fuel, you get about 175 megajoules out of 4 litres of fuel. Megajoule you might recognise as the unit of energy that they use to charge you for gas consumption. When we did the experimentation associated with my PhD, we used some research literature, and we also measured the amount of energy a car actually requires to be moved around. And it turns out that on average, only about 35 megajoules of that 175 megajoules actually propelled the vehicle around for that equivalent amount of use that represents the 4 litres. And so just simplistically, that comes out to be 20%. So you got 4 litres of fuel, which isn't very large. You know, it's a can of paint size amount of fuel. It's got 175 megajoules in it, but you only used a fifth of it to make the car move around. The rest ended up, or in fact, it all ended up as heat in the end, but most of it just comes out the exhaust and out the radiator as heat. So 20%, you think, oh, that's something that you probably could get better results from. So the classic thinking these days might be that we're going to solve this whole issue as soon as people start using electric vehicles. So if we make the assertion that if you take this same vehicle and you make it electric propelled, we can assume that it's going to use about this same amount of energy, about 35 megajoules to push it around for the day. In fact, that probably is a little bit optimistic. There is no doubt that an electric vehicle will weigh more, and if there's time at the end, we'll see some figures on some currently produced vehicles. So it's optimistic to claim that it's going to use this 35 megajoules, but we'll use that number because it's the conservative way to look at it. So actually, in the previous slide, I probably didn't mention, so 35 megajoules is a measure of energy. You can convert that into kilowatt hours. The kilowatt hours you see on your electricity bill. So 35 megajoules is very close to 10 kilowatt hours. So you get a bill that says you use 12 kilowatt hours a day. It's sort of similar in magnitude to the amount of fuel that you needed to propel your vehicle around if you did it at 100% efficient. So anyway, I'll go forward to this next slide. So we're assuming that we're thinking of an electric vehicle that's the equivalent. It's a usable, family-sized vehicle, has no trouble doing everything you want. It's going to use this 10 kilowatt hours in a day. So the question is, how efficient will that achieve the transfer of energy so you can propel your electrical vehicle around? So you would be fairly reasonable to assume you can do it at better than 20%, and you will be able to do it better than 20%, but how much better? So here's some more numbers. Unfortunately, engineer, we tend to think a bit in numbers. We need to consider a few energy transfer efficiencies to find out how much energy actually is needed to make this electric vehicle get propelled around. So at the power station, assuming that we're burning gas or coal, which is by far the majority of energy source that's currently used in Australia, and we do go further to suggest the outcome if we don't burn the fuel in the first place. We get 50% efficient in the power station, somewhat better than the 20% we get in a car engine, and that's primarily a factor of scale of magnitude and the fact that you can run it at optimum efficiency, whereas in the car you're not anywhere near its optimum efficiency most of the time. So then you get some transmission losses, especially if the distribution system is powered from isolated sources. If it's got distributed sources, you might get a bit more efficient than 90%, but that's also an optimistic estimate. And then you've got the battery charge and discharge efficiency. So you might recognise that when you when you charge up your mobile phone, it actually gets warm. So the energy that goes into the battery that you later on use, some of that is lost in making the battery warm. And then from the battery to the propulsion system in the car, they're quite efficient. 85% is probably just an average representation of that, and that is pretty dependent also on how much power is being transmitted. It's a little bit higher efficiency at low powers and lower efficiency at high powers. So anyway, you multiply all those together to find out the net efficiency of the transfer of the energy that was in the fuel that you burnt in the power station to the propulsive power that made your vehicle move, and you get 31%. So it's better than 20, sure, but it's not fantastically better, but certainly something probably worth pursuing. So the first question that skeptics of what I'm saying are going to say is, well, what happens if you don't burn fuel to get the power in the first place? What happens if it's renewable, solar or whatever source you get it from? Well, yeah, that's a legitimate complaint about my approach there, but there's a whole bunch of other things to take into account, and the most significant one is the battery life. Currently, and it will improve, you would have heard earlier today how the cost of, I think it was Tim Flannery, the cost of solar cells have come down by 75%, and that's manifesting cost of installations in Australia in the last 5 years. But the current cost of batteries of the type that can be used for propulsion in vehicles is not changing particularly quickly. Whether it will change is speculated that it will, but there's no real evidence that there's any really serious improvements to be gained. And that statement is also a little bit bland. Currently, you store, well, I'll revert and say you buy a $30,000 car. In its lifetime, you're going to use about $30,000 worth of fuel. If you buy an electric vehicle now, it's going to have about a $20,000 or $30,000 battery in it, but it's only going to have about $4,000 or $5,000 worth of electricity put into its life. So the battery is a very significant cost, and if you assert that cost is somewhat reflected in the energy that was used to manufacture the batteries, then you're going to say that there's no real efficiency in claiming, or there's no real legitimacy in claiming that you're only using $4,000 worth of electrical energy to power a vehicle for a lifetime, when in fact the batteries used $15,000 worth of energy to be made. So I'll carry on with my slides. So if we go back and we take those numbers that I used, except for the 50% efficiency in the actual generation, you multiply the 90, which was for the grid, and the 80 for the charge-discharge efficiency, and the 85% for the battery to propulsion efficiency, and you assume you're getting to need 10 kilowatt hours for your car in a day. Those numbers mean you have to pump 16 kilowatt hours of energy into the car. And unsurprisingly, that's very similar to the magnitude of the typical household power bill. And obviously, that's dependent too. You've got a couple of teenage children that might be significantly higher than that. But, you know, and if you've got hot water that's solar heated or whatever. But those numbers are similar, and that's an important thing. So, yeah, if you're considering that electric vehicles are going to solve a problem, then you're also considering doubling the electrical supply system, both network-wise and production-wise. So my next slide asserts that as a society we're predisposed to believing that technology will fix things. These things are really incredible. Like, I mean, as a mechanical engineer, I get astounded by what these things can do. Well, not all that long ago, I was using a GPS going along a motorway, took an exit, went past an 80 sign, and I was off throttle. I was just slowing down, maybe doing 90, and then a few seconds later, it was what was the phrase? It was alert, alert. And I was, what's this? And it was the GPS telling me that I was speeding. And I'm thinking, well, how can a system, how can a GPS extract from the ether that I just went past an 80 km/h zone sign? Well, the system is capable of doing it, and it's astounding that it can do it. And it is reasonable for people to believe when these sort of miracles happen that there's going to be a miracle on the transport, personal vehicle front. And unfortunately, I'm here to tell you that it's pretty unlikely. In fact, most probably legitimate to say impossible. So this next slide asserts the reason for that, and that is that power is power, energy is energy. You can't move a vehicle around without it. It doesn't matter what technology you employ to do it. That is some quantum leaps in efficiency better than what we currently do. There's still a substantial amount of power required to move vehicles around, and you're not going to be able to circumvent that. It's a fact of physics, a fact of nature, and a quick fix is not going to happen. So I just made up this somewhat simplistic categorization of the fixes that are potential solvers of the problem. And the first one, don't use vehicles. Well, the prospects of that are next to zero, but I mean, it's a legitimate fix, and that might be that webcast guy who was talking last. He might assert that that's the fix that's going to eventuate. The next one is don't commute. I mean, this is more feasible. Like, for example, I'd sit in front of a computer for 80% of the time I'm at work, so there's no real reason I can't do that at home. There's a reason that I do have to go to work, but if a bit of planning and a bit of organising, you could probably adjust that. So maybe spend 3 days at a home-based computer and 2 days in a work-based environment. The next one is human-powered vehicles, and they're only 3 stars. And you think, well, there's no power associated with that, but when you actually do the analysis, you find out that they're not particularly energy neutral. And one simple way of thinking of that one is you ride a bike to work and then you walk up and have a shower afterwards. The amount of energy that you use to have that warm shower is about the amount of energy that an electric bicycle would use to get you to work. So they're not completely power neutral. And we've gone down out of green fixes to an off-green, use public transport. And in Toowoomba that is not functional solely on the density of use. But in concentrated capital city situations, they are viable. And the last one, which is not even green anymore, it's a 1 star, is to improve the energy transfer efficiency. So in my case, my research produced this device, which is, and that's another bit of technology. This thing I've got in my hand was printed by a 3D printer. A piece of technology, you design it in a computer, you draw 3D models, you put it in a box, you press the go button, and this piece of hardware comes out the other side. It's quite incredible. So this device, a piece of machinery that potentially can change the efficiency of vehicles. Instead of your 4 litres a day, it might drop it to under 3.5. It's called a VLCR, Craig mentioned that, and potential small but possible You currently see vehicles, CVVT, continuously variable valve timing. One day you might see vehicles with VLCR on the badge. So the next slide is the fact that, in fact, in my workplace, 4 people, we all use bicycles. I'll qualify that in a minute. And it's another just image off the web. And you're thinking, what's the big black block for? It's not to minimise the security or the people that are in the car. It's to play this little video. Now you're thinking, what's he doing now? And if anyone knows what your anatomy looks like, that's a knee. And that, in fact, was my left knee a year ago. And that was a consequence of riding a bicycle. So if you look closely at that image, below the joint, that is not supposed to be the shape. So that is cost about 5 lifetimes worth of energy. So if you considered that you were going to use energy saving on your human-powered vehicle, I don't know what number of people have this happen to them, but you have to take that into account as well. So we have another minute or so. I did all this work maybe 2.5 years ago, and I wasn't absolutely certain that I was still seeing things that are current. So I went on the web yesterday, and an American boutique electric car manufacturer, you might have noticed them, Tesla, they became famous for making an electric sports car. They sort of initiated the concept, lots of other small companies followed. But now they've made a mainstream sedan, and they're advertising, perhaps not advertising, but I saw the article in an engineering journal, $50,000 US retail price, intending to sell 50,000 of them in 2013. The US government's currently supplying a $7,500 government rebate for it. Weighs 2,100 kilograms, got a range of 250 kilometres. Pay another $30,000 and you can up that range to 600 kilometres. It's a vehicle that's not dissimilar from a mid-size Toyota, an Avalon in the US at $33,000, weighs 1,600 kilograms. So the difference essentially is no different now than it was a few years ago. The difference is a 500 kilogram, $25,000 battery. And I won't go to the next slide, and that's all.